He's texting.
Do you want transition again?
Yeah.
You have to cut this part out.
You're on?
So now we're going to open it up and have a little more discussion and potentially more clarification if there's anything someone would like us to go back into. So Michael has contributed some criticisms that we can dive into, and Dave has some points of his own that could stimulate further discussion, but I'll introduce these three that Michael gave that are from a critical perspective. So one question was, what can we know or speculate about the impact of the progressive structure on modal collapse? So based on what they presented and what we know about the training, how can we infer something about whether this helps mode collapse, whether it exacerbates mode collapse? How does this play together? The second point is there's a lot of structure that's assumed. For instance, the fading in of layers. What can we know or speculate about the role of the pseudo-residual blocks and the training phase cycle structure of progressive GAN? Then the third point, again, structure. Oh, that's the same one. So, and Dave, maybe you want to say the point that you were thinking about?
So they mentioned adding on statistics, and I think I heard that it doesn't really matter what statistics are concatenated on. I'm kind of wondering this in open question, if anybody has ideas around statistics that might be potentially useful to add on, in addition to just say standard deviation, while still maintaining differentiability. So that's kind of one open question. Another question is, fading in, is there another approach with maybe smart initialization? Could there be something there? So those are a couple of points that I think I'd like to talk about. I could also briefly mention like how I tried this last year to implement this. I don't think I got it right because it destabilized every time. But again, I was using small batch sizes. The graphics card that I was running this on, I mean, it's a good graphics card, but the mini batches were limited in size for sure. So near the high resolutions, like going from 128 to 256 by 256, fading in a layer, I really only had the patience to do about 100,000 training cycles for these batches. So like I would try to do a fade in across that time period, and so I tried with just a linear interpolation, but I found that like about 5% of the way in, it would just break. Like it would just suddenly diverge, and the sample quality would deteriorate, gradients would go everywhere. So I also tried with a sigmoid fade-in as well, and ran into the same kind of issues as well. That's basically just following an S-curve where it's like a very, very light introduction at the start, but then it begins accelerating as it gets towards that 50% mark, and then fades back off. So it's difficult to implement. That's one thing that I can say. I think you've had potentially more success with this, or
yeah.
I
think I don't know what data set you were working with.
Yeah, so I was working with flowers. So flowers are not very well behaved. That's one thing that I've noticed. So.
Yeah. The nice thing about typefaces is that the latent space is usually really well behaved.
Okay. Yeah.
I just want to slip in another discussion point, which you mentioned earlier, the comparison between this guy and covariate shift.
Yeah.
I also want to slip in my clarification question, which I didn't get to. Like, I think that and if it's out of the patients, we can just talk about it offline. But I think that figure where you actually say, I'm concerned about the implementation, I think not all the detail was conveyed.
Okay.
So if you have the patients for
was it the first figure or the second figure?
The bad figure.
The second figure.
Yeah.
Okay.
Architecture.
Sorry?
The architecture.
I just want to see the implementation steps, because I couldn't see that from the figure.
So the code is not open source, right?
Yeah, you can look at the code that generated these results is there's a TensorFlow implementation.
The reason I mention it because if you want to talk about covariative and those things, well, I need to know the steps. Do you mind? So can we just go back before getting to this, just very quickly? Oh, it's not okay. My bad.
I think
So this one.
Yeah. So okay. So you're adding a layer.
Yes.
Therefore, you have some random weights to initialize your layer, and you're saying that these random weights would introduce a shock, right? And the way to sort of mitigate it is to have some of the information from previous layers pass on to this layer. How exactly does this last piece work?
Like in the implementation.
Yeah.
I mean, we can bring up the code. I have it on the next slide.
Okay, that may be too detailed. So how? Let me put it this way. So okay, so are we talking about the? Are you? What are the residuals? Are they weights or are they data generated pixels? Seems like it is data.
So here would be data.
Okay. Then how? So you have a 16 by 16 data, or then you do you upsample it. You sort of interpolate and fill in the gaps.
Yeah.
Then.
But it's going to be blurry when you upsample it at the
Correct.
start. And so one thing to keep in mind is, and this is probably where some of the instability in the network that I was training was, because I don't think I paid enough attention to the discriminator side. I'm pretty sure I got the generator side correct, but I think I might have missed it on the discriminator. And what you need to keep in mind is that the generator, sure, it's been doing high quality 16 by 16 samples, but now once you go to 32 by 32, you've got a discriminator that is suddenly getting 32 by 32 images coming in that are, high frequency, high resolution compared to the upsampled low resolution images. And so suddenly you have high frequency being compared to low frequency, unless you're taking specific steps to essentially fade things in, right? So you want to make sure that the higher resolution images don't suddenly throw things out of equilibrium. Assuming that the network was originally in an equilibrium state, so the discriminator got to a point where it was like, okay, I can't tell the generated 16 by 16s from the real 16 by 16s. It suddenly gets into a state where it's like, okay, there's high resolution versus low resolution images. I can immediately tell those apart. Suddenly it's completely out of equilibrium. Yeah. And then you no longer have these small micro adjustments being made to the network. It's suddenly major adjustments that are being fed back through the network, so you get these gradient spikes.
If it's only seeing the result of the activations on those filled pixels.
Yeah, so what I would do actually in this case is gradually fade in the real images. So like say you've got a 32 by 32 image, I would probably start with the 16 by 16 and the 32 by 32, upsample the 16 by 16 and fade that in as well, so that you don't suddenly introduce high resolution imagery to keep it in equilibrium. The whole idea is to always keep it in equilibrium.
Sure, but this is generated images. This is not real images, right?
So yeah, there's the
discriminator. It's real.
The discriminator gets to see both, right? The generator never gets to see any image. It just is told to turn random noise into high realistic, like photorealistic content, basically. So that's a very difficult job for it to do, and it only does that through the feedback that it gets from the discriminator, and the discriminator gets to see the real images and the images produced by the generator, and then provides feedback. But the whole time the generator's blind.
So just handing over a little bit of the residuals of the previous layer, which is just, again, interpolations, but it's not just an activation layer hasn't really processed it. You get a smoother sort of just by adding those two together. You get sort of a smoother transition from.
It's about smoothing it all out, essentially.
So it's like most of the generated are still not going through that 32 layer, while the real ones are still like coming on. So you have ones that are more similar, and then the ones going through the 32 layer, they're going to be like a lot more random than the ones that are just upsampled.
Makes sense.
And you have an equal but opposite process in the discriminator where you downsample? Is that
Yes.
correct?
That part is key, don't ignore that part.
Yes.
So Andrew, you tried to actually use this paper on your data set, the type fonts.
Yes.
Did you find it was better than other methods, what you guys were doing previously?
So the best method I have so far is using a kind of ResNet decoder,
Mm-hmm.
and then taking those results and passing them through a cycle GAN.
Okay.
I find this one, I still haven't gotten the training perfect, and as even recently have issues where it'll get pretty good and I'll run out of memory, or my GPU will crap out, and then I'll have to start again. So it's tricky. The training is really stable sometimes, but other times it's not stable.
So you're starting at like 4x4 and you're working your way up to what resolution eventually?
The biggest I've gotten to is 256.
Okay.
So it saves a lot of time once you get it right. But it can take a long time to get there.
Right. And one of the major criticisms with a lot of GAN papers is that they put really nice pictures in their paper, and then they make their code really inaccessible for one reason or another, whether it's the hardware requirement
Yeah.
or something else. Or I see in a lot of like GitHub repos people complaining, I can't recreate what you showed in the
Right.
paper, and that's mostly due to hardware or something in the training. Sometimes the implementation given is different than what they discussed in the paper. So I mean that's another like an issue which comes up here is that most people can't get this $200,000 equipment to actually
Yeah.
recreate the stuff.
Is it available on the cloud or anywhere?
You can definitely run it on AWS.
You run it on local machines?
No, I use a P2X on AWS.
Right.
But that has 12 gigs of GPU memory, and that can't make it past 256, even though the authors say you should be able to get to 1024 with a 12 gig GPU.
Right. And you're using the same code?
No, I'm not.
Okay, so just a quick, because I said earlier, just a quick note on covariate shift. So I think the idea, and correct me if I'm wrong, in covariate shift you try to normalize, in batch norm you try to normalize the weights as you go on, because once you, in gradient descent, once you update the weights, you're going to produce, because what you've learned before, you're going to produce a different sort of distribution because you changed the weights.
Yeah.
Each layer will receive a different distribution from the previous layer because of the changes in the weight. Right? So that's called the covariate shift. Right? And to make that distribution not vary as much, you normalize the weights right, as you go on. And how did it connect? I forgot how it connected to.
So that was introduced in the talk of normalization.
I think they use pixel-wise normalization in this paper.
Right. So yeah, it's in this one. So it's the spiking gradients point. So where they use pixelized normalization, that's what. So I guess they say the covariate shift isn't the problem; it's the spiking gradients that's the problem.
And then you clip for that.
So
yeah, exactly.
Keeping things in equilibrium is one good approach, but one kind of way to soften some of the gradients is, and I did a post about this a little while ago, to put them on a log scale. So if you think of the function log of 1 plus x, that's basically this like nice function that has a slope of 1 initially, so it's very much just like a straight identity mapping near the origin. But then when you start moving further along, it requires like exponentially more in the gradient to create just a linear addition to the transformed log scale gradient. And so I found backpropagating the log scale gradients was one way to essentially protect the network during training.
I have a question on the normalization here.
Yeah.
Do you have, is the next slide about normalization or is it just this slide? Normalize. Okay, so I can't wrap my head around this intuitively because it is arguing that basically generator and discriminator could, you want to balance them out. So that's why you normalize the weights. Is it the weights or the output?
Could you say it a different way?
The normalization, what is being normalized is the weights or the output layers.
I think it's like pixel-wise basically means that for a given layer, it's going to have a spatial dimension and then n number of channels. And basically what they're saying is that for pixel-wise normalization, where they're basically forcing all of those channels to sum up to 1, that's basically forcing them all into probability distributions in a sense, right? Pixel-wise. So it's interesting because it's not putting any constraints across the channel. It's just saying that the scale, the scale of those weights needs to. Actually, that's a good question. Is it on the data or is it on the weights? I would have to double check.
The equalized learning rate is on the weights.
Okay.
Pixelized normalization is applied
It's on the output.
On the output.
Okay, my question. Okay, but actually my question is, regardless, my question is, they are doing this respectively to the generator and the discriminator.
Pixelized
normalization. They want to balance things out.
This is only in the generator.
Oh, in the generator.
Yeah.
Was there a slide that talks about you normalize because you want the generator and discriminator to?
So that's more the standard deviation, which is trying to keep the
okay,
variance between the generator and the discriminator the same.
Oh, okay. No problem, Mr.
One thing that I found that really helps with quality here as well is in the final layer, the generator, if it's mapping to just like RGB values that are not scaled, that then get scaled, right? So if you're just basically asking it to predict regression values, right? Where it can be like essentially any integer, lots of gray will appear in the image. Putting a sigmoid on the color channels of glass layer tends to be a really great way to improve quality because it constrains things. Yeah.
That's good.
So for the standard deviation approach, I think you said the idea was that they're taking the variance in each pixel across the batch that's being fed in. Is that correct?
Mm-hmm.
So what does that really represent when the batch size gets reduced to 1?
So it's not very meaningful at that point.
You're literally just feeding in the
Yeah, you're just
image.
feeding in the standard deviation of the image.
Okay.
So for the equalized learning rate, it's very confusing because in the paper they talks, okay, we're not gonna use any special weight initialization. We're just gonna use like a trivial.
Right, they just use ease and
then they say this helps with getting an equalized learning rate. Well, how?
So when they're defining the parameters, they're looking at. I had to go into the code to make sense of this part of the paper. So they look at the number of feature maps in the tensor that's going to pass through that layer, and then they take the product across that feature map, and that's what they call the dynamic range. Or that's what they use to compute this equalized learning rate, and then they multiply the weights of that layer by that scaling factor. Okay. So
you have 2 minutes.
Maybe cover any other points in your last slide.
Yeah,
that
1 minute.
is it in the last slide?
Your
Like
discussion
points.
points.
Yeah. So what can we know about the impact on modal collapse? There's no strong evidence of mode collapse in the results that they've released. The data is so complex though and so multimodal that it's still really difficult to evaluate it. I know that in the previous talk on StackGAN there was a TSNE projection in 2 dimensions that showed the latent space was evenly covered. Something like that could be really interesting here. I'm not sure if you have any thoughts on it, Dave.
So I have a lot of experience with mode collapse. It tends to happen all the time. One good way around that I found is basically, mentioned this just earlier, is to compute the pairwise distance at the discriminator. When you get the features, prior to actually making the decision based off of that final layer of features, what you can do is essentially measure the pairwise distance of each of the real samples and each of the generated samples. So given, say you have a mini batch of like 64 images, they're going to represent 64 points in space. And so if you then try to, if you then compute the average distance between each point and every other point in the one cloud, and each point and every other point in the other cloud, like real images, generated images, you can then add the difference between those two as a term to your loss function. So you've got your standard loss function, whether it's Wasserstein or least squares, whatever it might be. Add on an additional term that is comparing the pairwise distances to make sure that those two clouds approximate the same size. And that seems to be accomplishing a similar effect as to adding on statistics, like concatenating them on. Yeah, there's a whole interesting discussion around that, especially like when it comes to whether or not you consider each sample as being one large vector, or if you divide up the features in the last layer into subspaces and consider it a set of vectors that are all then individually compared, so making sure each of the individual subspaces all have the same average distance. Those are different approaches that have like different geometric implications, but adding on that kind of term does actually help quite a bit. I'm using it in CycleGAN. I ended up starting to use that after this paper, and it's been good for avoiding mode collapse.
So I think that's all we have time for. We can thank Andrew one more time.